These sums of squares suggest Pythagorean theorem with a shared hypotenuse. So that might look something like this. This will be the hypotenuse, and the legs will have lengths A and Y with a right angle here. B is less than A, so we'll draw another right angle here. So we have this quadrilateral. I'm going to call it PQRS. These opposite angles at Q and S are both 90 degrees, so this is actually a cyclic quad. Let's redraw it inside of a circle. Here's the diagonal PR, and it looks like we have X is less than A and Y is less than B in this sketch. PR is our shared hypotenuse, so it's A squared plus Y squared and B squared plus X squared. But in the problem statement, we also have that it's the sum of these squares. So we'll expand these. I'll match up the A squared and the Y squared, and we have this B squared and X squared, and I'll factor out 2 from these last two terms. And I'll substitute the square of PR for A squared plus Y squared, and the same thing over here. This AX plus BY is the sum of the products of these opposite sides of a cyclic quadrilateral. You might recognize this from Ptolemy's theorem, which has that AX plus BY is going to be the product of the two diagonals, which are PR and QS. So I'll do that substitution here. I'll also combine all of these PR squareds and divide by PR and solve for QS, which is 1/2 the length of this diagonal. Since we have right angles at Q and S, on opposite sides of PR, we know that PR is a diameter of this circle, so this distance is 2 times its radius. So the length of the other diagonal is the radius. Let's redraw these points so we can see what this means for our quadrilateral. Here again is PR, the diameter of this circle. Our other two vertices, Q and S, are separated by a distance that's the same as the radius. I'll just put Q over here. So these 3 distances are the same. If O is the center of this circle, we have triangle OQS is equilateral, which means the central angle QOS is 60 degrees. When I draw in these other side lengths of our quadrilateral, we find this inscribed angle QRS is going to be half of the corresponding central angle, or 30 degrees. And because this is a cyclic quad, the opposite angle QPS is 180 minus this. So this is 150 degrees up top. Let me redraw this once more. We're interested in the ratio of the lengths A and B, which is probably going to be related to this angle theta, which is QSR. And by angle sum on triangle QRS, we have angle SQR is 150 minus theta. We can relate A and B with the law of sines on triangle QRS. So A over the sine of theta is B over the sine of 150 minus theta. We can solve for the ratio A over B, and we need to pick a value of theta that maximizes this ratio. Recall that these angles at Q and S were 90 degrees. So for example, this angle on the left, 150 minus theta, it's a part of angle Q in the quadrilateral, so it's going to be smaller than the 90 degree angle. Solving for theta, we have that it's greater than 60 degrees. Likewise, with this angle theta on the right, that's part of this right angle PSR. So theta is going to be less than 90 degrees. So we need to pick a value of theta in this interval that maximizes this ratio. As theta varies from 60 degrees to 90 degrees, we have that its sine is strictly increasing. But on this interval, as theta goes from 60 to 90 degrees, 150 minus theta goes from 90 degrees to 60 degrees. So its sine is strictly decreasing. We want to maximize the numerator and minimize the denominator, and these coincide when theta approaches 90 degrees. This will be our maximum value for the ratio. The problem asks for the square of the maximum value of the ratio, which is 4 over 3, and the sum of m and n is 7. If you'd like me to solve any other math contest problems, please leave them in the comments.